relating to spectral response at a shorter wavelength region. Cadmium sulfide is transparent so that cadmium telluride can absorb the greatest amount of light. It has a bandgap of 2.45 electron-volt, conductivity of about 10 to the power of 16 centimeter per cube, and thin thickness between 50 to 100 nanometers to allow high transmission for high efficiency solar cell. As an active layer of the heterojunction, the resistivity of cadmium sulfide must be small for good ohmic contact with the TCO layer, as I have said before. Furthermore, cadmium sulfide is used to establish an electric field at the heterojunction interface that collects the photo-generated charge carrier. Therefore, the electric field produced at the cadmium sulfide cadmium telluride interface should be high to improve the open circuit voltage. However, one problem with cadmium sulfide is that it results in significant loss in field factor and open circuit voltage when the thickness reduced too much. This will result in the cadmium telluride layer directly contacting the underlying oxide layer, weakening the junction average quality and decreasing cell performance. Therefore, a buffer layer called high resistive oxide is deposited between TCO and cadmium sulfide, as in the diagram, to overcome this problem. Next. Next is high resistive oxide is a buffer layer with electrical resistivity in the range of 10 to the power of 2 to 10 to the power of 5 ohm centimeters. It is usually added in the cadmium telluride solar cell technology. The buffer layer allows a thinner layer of cadmium sulfide to be used. One proposed reason is that the space charge on the N-type side of the junction can expand into the buffer layer when the cadmium sulfide becomes too thin to balance the charge needed to maintain the space charge width on the P-type side of the junction. This enables the space charge in the P cadmium telluride region to remain sufficiently wide as the cadmium sulfide is thin. As a result, it can avoid device functionality dominated by voltage-dependent collections such as low field factor due to loss of minority carrier collection and high forward bias. The buffer layer also reduces surface recombination at the cadmium sulfide TCO interface, resulting in less detrimental device performance as thinner cadmium sulfide layer position this interface closer to the junction. High resistive oxide also helps decrease the possible diffusion of atoms from the TCO to the rest of the film in the device. The graph shows enhancement of the quantum efficiency at most wavelength when the high resistive oxide is used, indicating the absorber improvement of light capture and carrier transport. Next. Next. P-type cadmium telluride is the most important part of the device with an absorption coefficient of greater than 1 times 10 to the power of 4 per centimeter, allowing 90% absorption with 1 micrometer thickness of the thin films. Cadmium telluride formed from group 2 and 6 element, which is cadmium and tellurium respectively. It also has a zinc blade structure, which is most likely like diamond cubic. Cadmium telluride has a direct bandgap range of 1.5 to 1.5 1.45 to 1.5 electron volt, optimal for the solar spectrum to deliver efficiency around 32%, just like Azwani had mentioned before. The graph on the right shows a Shockley and Quasi curve for cadmium telluride absorber. In addition, cadmium telluride has an open circuit voltage of more than 1 volt and a short circuit current greater than 30 milliampere per centimeter square. Carrier lifetime for cadmium telluride is small, of the order of 1 times 10 to the power of negative 7 seconds or less, with mobility ranging from 10 to 100 centimeters square per volt seconds. Cadmium telluride also has a high metal contact of 5.7 electron volt, which will affect the semiconductor metal junction. The average module efficiency of cadmium telluride solar cell in 2019 is above 16.4 to 22%, slightly less than silicon-based photovoltaic. The picture on the left is the SEM micrograph showing a cross-section of cadmium sulfide cadmium telluride superstrate device produced by NREL. Next. Next. So the last layer of cadmium telluride superstrate structure is metal, a back contact collecting the charge carriers as the absorber side and the contacting the cell with the external circuit. An ideal back contact should have a p-type conductivity and a voltage greater than the cadmium telluride. However, one of the long-standing cadmium telluride solar cell challenges is it has a high work function. Most of the lower work function metals create a Schottky function at the cadmium telluride metal interface. This generates a potential barrier and owing to the resultant barrier. When a high forward bias is applied, the back contact dominates and the current through the solar cell becomes limited, resulting in the flattened IV curve. This can result in lowering of fill factor with increased barrier height as shown in the graph. Significant research has been undertaken by heavily doping the cadmium telluride layer at the back surface with a suitable metal, such as copper, to make it effectively P+ region, forming a pseudo-ohmic contact. Further improvement is made to gain a higher structure efficiency by deposited zinc telluride between cadmium sulfide and metal contact. It also forms a pseudo-ohmic contact when doped with copper and limiting the recombination loss of the minority carriers. That's all for me. I will pass it to the next member.
Hi everyone. So I'll continue the part of the heterojunction of cadmium telluride solar cell. So has been mentioned by Raihan in details just now that the most common cadmium telluride solar cell consists of p-n heterojunction structure that containing a p-dope cadmium telluride layer matched with an n-dope cadmium sulfide or magnesium zinc oxide window layer. So this heterostructure is usually preferred because of the minority diffusion length of electron in a p-type semiconductor that has a much greater than a holes in the n-type semiconductor. As the result, this solar cell perform faster recovery from the induced damage, presumably due to the strong defect compensation effects in cadmium telluride. So So the next is cadmium telluride activation treatment. Cadmium telluride activation treatment is a post-deposition treatment of cadmium telluride that is necessary to obtain high efficiency. This is irrespective of the deposition method or the configuration of the solar cell itself. And the crucial point is that the effect of chlorine on the cadmium telluride properties in a reaction at high temperature. This chlorine is delivered on cadmium telluride in a wide variety of different ways. And the most common procedure is the cadmium chloride deposition on cadmium telluride, subsequent annealing. That is also known as cadmium chloride treatment. Cadmium chloride treatment is a standard and vital process in fabricating high efficiency of photovoltaic device. And this cadmium chloride treatment by wet method involve two processes. The first one is dipping of cadmium telluride layer in a cadmium chloride methanol or cadmium chloride water. And next, the process goes by the cadmium chloride layer is deposited on the cadmium telluride followed by annealing. So generally, the process is like the cadmium chloride layer deposition on the cadmium telluride is formed by immersing a thin film in a cadmium chloride solution. And then subsequently, annealing can be applied in air or in controlled atmosphere at a temperature in the range of 400 to 500 degrees Celsius at the desired interval time. And lastly, after the heat treatment, the sample is washed with water to remove the residue of the cadmium chloride. As the result for this treatment, optical analysis shown about 15% decrease in the transmittance of the cadmium chloride heat treatment in the case of the cadmium telluride thin film, whereas for the cadmium sulfide thin film demonstrate an increase for about 10 to 15% transmittance after the cadmium chloride heat treatment. A decrease in band gap values was found in both cadmium telluride and cadmium sulfide thin films after this cadmium chloride treatment. So for this treatment itself, it has the disadvantages and advantages. So for the advantages is this treatment is a non-vacuum procedure. So it is very simple and very inexpensive. And it is also easy to disposal and handling of the ring set. And it is also can improve the short circuit current and open circuit voltage through enhancing the crystallite grain nucleation in the cadmium telluride. So for the disadvantages is that the surface treatment is only effective for small cell fabrication and fails for large area manufacturing due to the non-uniform distribution of cadmium chloride and processing in a humid environment leading to the cell degradation. And the next one is the residue of the cadmium chloride itself may not be completely eliminated by washing, as the formation of the water as the formation of water insoluble oxychloride can stick to the film. So next one is the new cadmium telluride solar cell structure. So has been as been mentioned earlier by the past presenter many times. So we all know that the average module for the cadmium telluride is only about 16.4%, which is slightly less than the silicon-based photovoltaics. But recently, the newest technology has been produced, and the efficiency was over 22%, and this was obtained by a specific engineering for the junction. And the first one is the cadmium selenide tellurium, and that is for the introduction for the cadmium telluride band gap grading. And the second one is the magnesium zinc oxide introduction for high transparency. So these two strong innovation has been revolutionized the cadmium telluride solar cell. The cadmium selenide tellurium, that is for introduction for the cadmium telluride band gap grading. the cadmium selenide itself can enhance the quantum efficiency response. And the mixing of cadmium selenide and cadmium telluride layer by the activation treatment can form a photoactive cadmium selenide telluride compound. And this mixing has a narrower band gap than pure cadmium telluride, so that the lower energy photon are also can be collected. And this cadmium selenide telluride compound has helped to increase the photocurrent by lowering the energy band gap, but without commensurate open circuit voltage loss. This is attributed in the part to longer carrier lifetime relative to the cadmium telluride on the absorber. And for the second one, that is magnesium zinc oxide introduction for the high transparency. So magnesium zinc oxide itself is a promising alternative window layer material that has a higher band gap grading to improve the photocurrent. Magnesium zinc oxide also improve band alignment with cadmium sulfide, and this magnesium zinc oxide also can tune by substrate the temperature, controlling at the same time the magnesium content. Do you guys remember that, right? Sorry. Oh, okay. You guys remember, right, that Raihan just mentioned that the common solar cell configuration is superstrate, but it can also be fabricated in substrate configuration. So substrate configuration is the deposition sequence is reversed and the stack is formed on a substrate, which does not have to be transparent. But this substrate configuration is not commonly used compared to the superstrate, because to attain the high efficiency for the cadmium telluride cell in substrate is quite challenging, and this device design requires a formation and retention of low resistance back contact while attaining a high quality cadmium telluride film and conjunction. So that's all from me. I'll pass to the next presenter.
Okay, thank you, Izzati. My name is Norshisha Izzati binti Muhammad Khalid, and I'm going to present on operating principle. Next slide. Okay. Cadmium telluride is a stable crystalline compound formed from cadmium and tellurium. It is mostly used as the semiconducting material in cadmium telluride solar cells. It is usually sandwiched with cadmium sulfide to form a PN heterojunction solar photovoltaic cell. Next slide. Just now, Norahan Shamimi mentioned about the structure of cadmium telluride solar cell. Here, I laid the schematic of typical cadmium telluride solar cell. As we can see, the first region is a glass substrate with anti-reflection coating, which helps increase the amount of light absorbed into the cell. The second region is a transparent conductivity oxide. Properties of transparent conducting oxide are good electrical conductivity and optical transparency, so that photons can pass through it. Cadmium sulfide and cadmium telluride are heterojunction structure. Despite the lattice mismatch at 10%, this heterojunctions has electrical properties leading to field factor of 0.77 and efficiency up to 16.5%. Region 5 has metal contacts for conduction process. As mentioned just now, the most common cadmium telluride solar cells consist of a PN heterojunction structure containing a p-doped cadmium telluride layer matched with a n-doped cadmium sulfide or magnesium zinc oxide window layer. Intermediate layers such as cadmium sulfide helps in both the growth and electrical properties between the transparent conducting oxide and cadmium telluride. The cadmium telluride layer is a p-type dope and its thickness is typically around 3 to 10 micrometer or about the 10th of the diameter of a human hair. Generally, the carrier concentration in cadmium sulfide layer is 2 to 3 orders greater than that of the cadmium telluride layer. Typical cadmium telluride thin film deposition techniques include vapor transport deposition and closed space sublimation. Cadmium telluride absorber layers are generally grown on top of a high-quality transparent conducting oxide layer, usually fluorine-doped tin oxide. Cells are completed using a back electrical contact, typically a layer of zinc telluride followed by a metal layer or a carbon paste that also introduces copper into the rear of the cell. Transparent conducting oxide layers such as tin oxide or cadmium stannate are transparent to visible light and highly conductive to transport current efficiently. Okay. What happens when a photon hits a solar cell? When a light photon hits a solar cell, it knocks free an electron that drives an electrical photovoltaic circuit. Considering that cadmium telluride is a direct band gap semiconductor and it has a high absorption coefficient, photons with short wavelength of 500 to 800 nanometer are mostly absorbed in cadmium telluride near the light incident front cadmium sulfide cadmium telluride interface. Next slide. Okay, how does a cadmium telluride solar cells works? Solar cells that use semiconducting materials needs to achieve two basic tasks. First, the absorption of light energy to generate free charge carriers within the material, and second, the separation of the negative and positive charge carriers to produce unidirectional electrical current through terminals that have a voltage difference between them. The separation function mentioned is usually achieved by PN junction, the interface regions of material that have been doped with different impurities to give an excess of free electrons, N-type on one side of the junction and a deficit of P-type on the other. The interface region therefore has a built-in electronic field that sweeps electrons one way and holds the other. In other words, a solar cell is an illuminated large area diode. Okay. Cadmium telluride film acts as primary photoconversion layer and absorbs most visible light within the first micron of material. Between cadmium telluride and transparent conducting oxide layers form an electric field that converts light absorbed in the cadmium telluride layer into current and voltage. Metal is placed on the back to form electrical contacts. These layers are deposited on incoming glass and processed into a complete solar panels in just few hours. By other means, when the sunlight falls on the cell, the electron gets excited and the boundary layers collapse to form a current. Next. This figure shows the main process. First, photons enter the cell volume through the front surface and are absorbed strongly close to the cell surface, but those from the other end of the visible spectrum are weakly absorbed and penetrate more deeply. Each absorption of photon converts the photon and transfers its energy to an electron in the semiconductor. It frees the electron from its parent atom and leaving behind a positively charged vacancy known as hole. In some materials, known as direct bandgap semiconductors, the absorption involves just the photon and the created carrier pair. But in indirect bandgap semiconductors, the process also needs one or more photons to take part. The electrons and holes are mobile within the cell and will move in response to an electric field or to regions of lower concentration by diffusion. They are also prone to recombination with each other. Next slide. Cell theory usually concentrates on minority carriers, electrons in P-type material and holes in N-type, since their flows principally determine the performance. Electron-hole pairs generated near the junction are split apart by the strong electric field. Minority carriers that are generated too far from the junction to be immediately affected by the junction field can be transported to the junction by diffusion, due to the minority carrier population being reduced near the junction by the field action there. Metal contacts at the front and rear of the cell allow connection of the current to a load. The front contact is normally in the form of a fine metallic grid to reduce blockage of the light's access to the semiconductor. The result of these processes is a light-generated flow of current in what is normally thought of as the reverse direction in diode theory. For example, electrons flow out of the cell into the circuit from the N-type contact and back into the cell through the P-type contact, even though the voltage across it is in the forward bias direction. The light-generated current is approximately independent of the voltage across the cell. From the figure, we can see that solar cell is exposed to photon particles in light and electrons holes become excited. The PN heterojunction for the depletion region becomes stronger, quickly sweeping negatively charged electrons and positively charged electrons holes across the barrier, creating electrical current. Electrons gravitate towards the external load to flowing around the circuit to create power. Next slide. How long can a cadmium telluride solar cells last? As a general rule, solar panels last for about 25 to 30 years. However, this doesn't mean that they stop producing electricity after 25 years. It just means that energy production has declined by what manufacturers consider to be a significant amount. Solar panels will continue to work for many decades, given they aren't physically damaged by wind, debris, or any other external factors. This is primarily because solar panels don't have any moving parts, so they rarely break from within and are usually only damaged by outside forces like a poor racking setup or inclement weather. That's all from me. Thank you.
Okay, thank you, Shasha. Okay, for my part, I will explain about application of the device. Okay, do you guys know that cadmium telluride is also used for farming, and one of the big project farming that use cadmium telluride solar cell is Topaz Solar Farm. Okay, it is located on the northwestern corner of the Carissa Plains. It used 9 million thin film cadmium telluride PV panels. It also designed and manufactured by First Solar, and it is owned by Berkshire Hathaway Energy (BHE) Renewables, and it is complete in March 2015. Next slide. Okay, it is produced sufficient electricity to power approximately 180,000 average California homes. It used 550 megawatt PV power station. Topaz Solar Farm is one of the world's solar farm. It also generates electricity with no emissions, no waste production, no water use, and has the smallest carbon footprint of any PV technology. Okay, it also, as you can see in the figure, it is used PV module that are mounted at 25-degree angle. It is for to capturing maximum sun exposure. Okay. One of the company that famous with cadmium telluride solar cell in Malaysia is First Solar Company. Okay, the location of this company is at 8 Jalan Heritage 3/3 and Phase 3, Kulim Heritage Park, 09000 Kulim, Kedah. Okay, what did the company do? Okay, First Solar is halting production and development of its new silicon product and returning to its historic focus on cadmium telluride. Okay, there are a few achievements that First Solar achieved. Okay, one of the achievement is in 2011, First Solar has set another world record for cadmium telluride photovoltaic module conversion efficiency, achieving 18.6% aperture efficiency for an advanced full-size module. For the first time ever, First Solar has demonstrated a record module that is more efficient than the best multi-crystalline module record. Alright, the next achievement is in 2015, the success of the company cadmium telluride roadmap reflected in their record 22.1% cell efficiency, along with the proven higher energy yield and superior performance inherent in their thin film technology that hedge is no longer needed. Okay. For the latest work update from First Solar is cadmium telluride thin film solar panel manufacturer First Solar has been developing a new solar module technology that use less copper, which result in low module degradation rates, and the name given is the Series 6 CURE. Okay, Series 6 CURE builds on the success of First Solar Series 6 technology, a large format thin film module. The Series 6 CURE module technology feature a negative 0.2 0.8% temperature coefficient, which improve upon the existing Series 6 baseline. Okay, there are some advantage and disadvantage of cadmium telluride solar cell. Okay, for the advantage of cadmium telluride solar cell, okay, first, cadmium telluride solar cell is low cost manufacturing, which is cadmium telluride solar cells use high throughput manufacturing methods to produce complete module from input materials in a matter of hours. Okay, next, cadmium telluride solar cell also high absorption, which is cadmium telluride is a direct band gap material with band gap energy that can be tuned from 1.4 to 1.5 eV, which is nearly optimal for converting sunlight into electricity using a single junction. Okay, next, cadmium telluride is also abundant. It is produced by a byproduct of the important industrial metals such as zinc, and it also has no the wider price swings. Okay. The fourth is cadmium telluride solar cell also environmentally friendly because it is produced little part of carbon footprint and has the lowest water usage and even has the shortest energy payback, which is less than 1 year, and unlike any current photovoltaic technology. Okay, the last is cadmium telluride solar cell also in part of efficiency, it is better efficiency at low level of illumination and high temperature. Next. Okay, the disadvantage of cadmium telluride solar cell is tellurium supply. As we know that tellurium is an extremely rare element which is hard to find because it 1 to 5 parts per billion in the Earth crust. Okay, next, toxicity of cadmium telluride. Cadmium telluride is toxic if it ingests. If it does, then it is inhaled, or if it is handled improperly, such as without appropriate gloves and other safety precautions, and it can become dangerous. That's all from me and my group. Thank you. If you have a question, you can ask.
All right, thank you, group number 7. Let's move on to our Q&A sessions. Okay, any questions from anyone? All right, from Fakri Hadi, I want to ask, what is CURE, C-U-R-E stand for in Series 6, C-U-R-E, or is just a name?
Oh, okay. I will answer her question.
Okay.
Okay. Solar Series 6, CURE, which is CU stand for copper, and RE stand for reduction, which is in this series, for Solar Series 6, they use use less copper for low degradation rate. I think I can only explain that.
So sorry, where is the copper in the device? Which layer?
I think
So it's copper reduction, right? So
yes.
where is the copper in the layer? In which part do you get the copper? Can you guys go back to schematic on the device or something? Where do you show layer materials? Yeah, anyone will do. Where do you have the copper in the device?
In metal.
Metal contact, is it?
Yes.
What's your metal contact? Can you go to the slide where you show every single layer? Metal contact slide. Yeah, okay. So the metal contact is purely copper or it's alloyed copper with something else?
I think copper.
It's just copper? Or
Is it for the first solar?
yeah, for the first solar process. So where is the copper? Or is it a pure copper black contact or is it alloyed copper with something else?
It's usually a alloy that with copper and gold, basically most commonly used.
Okay. So copper gold as your back contact.
Yeah.
Yes.
All right, okay. So next questions. Right, Hasnain, for working principal part, cadmium telluride is the absorber and cadmium sulfide is the window layer. The question is, can cadmium sulfide be an absorber as well in thin film solar cells?
Thank you, Hasnain. Cadmium sulfide can be absorbed in thin films, but before the deposition, any electron transporting layer should be on a substrate first, right? And the substrate that need to be used if cadmium sulfide is the absorber, the substrate is fluorine dope tin oxide, or you can use indium tin oxide.
So in that case, do we still have to use cadmium telluride or purely cadmium sulfide as the absorber? The one that you mentioned now, Shasha.
We can use cadmium sulfide as the absorber.
So cadmium telluride is out of the cell.
Yes, if we change the cadmium sulfide as the absorber, so cadmium telluride is out of the cell.
Okay, what was the band gap of cadmium sulfide? The band gap, I think you showed a slide of window layer or something, all right? Did you mention anything? What's the band gap there? Of cadmium sulfide?
2.45.
Is it optimum for light absorption from the solar spectrum?
No, it's too high for that.
Too high, right?
Yeah.
So then, can it be a pure light absorber?
Pure light absorber, no.
So you still have to have another layer to do the light absorption, right?
Yeah, which is maybe I have read somewhere that the P type can be CDS and the N type can be cadmium telluride, but the efficiency is not that high.
Okay, but in that case, you mentioned which layer is the absorbing layer, the telluride or the sulfide?
Sulfide.
Or sulfide, despite the high band gap.
Yeah.
So that's probably the reason why the efficiency is not so high. Because if you look at the optimum band gap for what's the optimum band gap again?
Sorry.
The optimum band gap. Yeah, what is the optimum band gap for light absorption in solar cell?
1.45 to 1.5.
1.4 to 1.5, right? And cadmium sulfide is 2.4. So it's not, if you recall last time we discussed about the bell-shaped curve, if you go for a high band gap, then you're gonna get high voltage, low current. If you're gonna go to low band gap on the left, you're gonna get high current but low voltage. And the optimum is in the center of the bell curve where you get a high current and high voltage. So when you design your band gap of the solar cell, it has to be somewhere 1 to 1.5 for outdoor harvesting. Okay. Right. Any other questions? Okay, Haziq. I want to ask you what happens to the disposed solar cell. All right, this is more on the disposal and waste management. Do they end up in landfills or recycle? If recycle, how? Any ideas? Do they end up in landfill or recycle? If recycle, then how? Okay.
So for this false solar cell, right? It actually it must be recycled because as mentioned just now that cadmium itself is a very toxic material. So it must be recycled in a proper way so that it does not pollute the environment. And the tellurium itself is a rare material and it is rare but it is not very commonly used for other things. So as long as we keep recycle the existence this solar cell, we should have enough supply of the cadmium telluride in the future. But for the recycle, I don't know how they recycle it.
But are we doing the recycling now, or are we just throwing them into landfill? What do you think?
Uh, I think they do recycle.
Yeah, they do.
Yeah, they do recycle. Because
Okay, go ahead.
um,
Izati?
because from my reading, there is an article that say according to the Department of Energy, it is important for for this type of solar panel to be recycled because and the first solar company itself are setting up the comprehensive recycle program for their own product.
Exactly. Yeah, exactly. So how about silicon then? What do you guys think? Well, out of scope though, it's not your task. Do you think we are recycling silicon panels or they end up in landfills? At least for Malaysia. Agak-agak lah. This is beyond the scope lah. But what do you think? We still don't have a proper one. We still don't have a proper recycling program for silicon. So I've been stressing to the ministry multiple times already. It's because we just had our solar farms like a couple of years ago, quite recently, relative to other countries, and we still don't have a proper recycling and disposal program in place for silicon. And it's not treated as urgent because silicon is not toxic if you compare to cadmium telluride, where it has to be compulsory before the plant is set up, just like what Izati says now, exactly that. Yeah, but plants are going to fail. Panels are going to fail, even though the plants are guaranteed to run and to be reliable for like 20, 25 years. And we do have panels fail in like 5 years or 10 years for various reasons, okay? Various reasons. So we have to be ready, and we are not yet ready for that. And it's dangerous for Malaysia, actually. So this one is more towards the decision making and ministry kind of work lah. Cumanya we have to realize that it's not properly in place yet. Because we don't have a major failure. So bila tak ada failure ni macam semua orang pun relax ya. So when it fails, then kita akan terkejut lah. So now I think probably they don't end up properly as far as if you compare to cadmium telluride. Cadmium telluride is very proper because the material is toxic in the first place to begin with. So that's why the disposal program, the recycling have to be set up before the manufacturing can be started. Okay, so exactly your answer. Good. So any other questions? Okay, I got an easy question, Darwina. Is there any material other than cadmium sulfide being tested for the window layer or for any other purposes, Darwina? To replace cadmium sulfide specifically in the solar panel? Okay. Do you guys know any other materials being tested other than the cadmium sulfide?
Yes, there are other materials that have been tested, but cadmium sulfide has been found to yield the highest device performance.
Okay. Would you mind to share what are those materials, if you know?
I
Is it
couldn't recall.
cadmium based as well, or completely different material?
If I'm not mistaken, completely different materials.
Right. So, well, for your information, the key concern with this technology is the cadmium. The toxic one is the cadmium. So, in fact, quite a number of countries rejected first solar due to the cadmium nature. Okay, but we accepted, and US is also running cadmium first solar operation because they are the HQ anyway. Provided they have to have proper disposal program in place. Okay, so the key concern with this product, with this technology, is the cadmium, but it's doing the job very well. So it's doing the job well at light conversion and stuff, but it's toxic to begin with. All right, so therefore the program has to be properly in place. So how about well, I think if you do some research, some reading for the window material, as long as the key concern here is as long as you have good band alignment with cadmium telluride, and then the window layer has similar band gaps of about 2 point something, just like 2.3, 2.4 for cad sulfide. They should be qualified to be as a window layer in cadmium telluride solar cell, but it's a matter of whether or not it can result in high conversion efficiency of the cells, just like what Hazwani said. The best one for now for this particular combination is cad sulfide. Okay, so any other questions? Do you guys know what's the doping levels in the layer, in the PN junction? What is the doping level in the cad telluride, cad sulfide, TCO? Any ideas? I saw something like two to three order of magnitudes higher than somewhere just now. Do you know what's the typical range of, say, cadmium telluride? Do we have anything here? Doping level? Do you have anything? Yeah. What do you think is doping level in cadmium telluride? So we learned about 10, 14, up to 10, 19, 10, 20. So what do you think is there for cadmium telluride? Agak berapa yang optimum? Just right. Okay, all right. You don't know. You found anything, Haswani? Anyone found anything? Better nanti you interview for solar. You go for solar interview for internship or for career for your first job. So these are among the things that you'll probably be asked: thickness, doping level, resistance, all the stuff, PN junction combination, the materials involved in the layer. Right. Tak apa lagi cari ya. Hold on, I have one more question, I think. Hold on. Okay. Cadmium chloride treatment. Someone mentioned about grain nucleation in cadmium telluride. So what is it actually doing? I couldn't remember who said. Was it Isati? Cadmium chloride treatment. Somewhere.
Yeah.
Okay. Nucleation of the grain. So how does it help? What is it actually doing?
The cadmium chloride treatment, is it the beneficial effects of the cadmium?
Yeah. Yes.
That actually, from what I read, there is actually lots of benefits from this cadmium chloride treatment, and for example is the recrystallization It can reduce the optical loss, strain recovery, grain growth, and grain coalescence. And it can also interdiffusion enhance, leading to the formation of the cadmium selenide tellurium.
Okay, all right. So do you want the grain to be big or small? If it helps in terms of grain growth, so do you want the grain to be big or small? Based on what we learned before.
Big.
Big, right? Why do you want it to be big? If big, then, or if small, then. My last question, 201 already. Kenapa kita nak grain besar? Based on what we learned last time. Carrier extraction and all the stuff. Yeah, Haziq mentioned recombination. So if grain is big, then what happens to the recombination? Do you want high or low recombination?
As recombination, as the grain grows big, the recombination is less. So
Less,
that-
right? But dia punya border between the grains will be smaller, right? Kalau you ada thickness yang sama, 2 to 5 micron, let's say 2 micron. Satu grain kecil. Then you're going to have more grains, right?
Yeah.
For the same thickness, you're going to have more grains and therefore more boundaries. Lagi banyak border lah, macam PKPD lah. PKPD you kena dawai-dawai banyak kan, tak boleh keluar kan. Sangkut, pergi sangkut, right? So, on the other hand, if your grains are bigger, if your PKPD area is way bigger, then you punya boundaries will be lesser over the same area, right? Then you will not, you takkan langgar the border lah. Then therefore the carriers will experience less recombination. And that will be good for the device in terms of the VOC especially, open circuit voltage. Right, so that's the final question. Let us give a big round of applause to group number 7 on cadmium telluride. Good job. Virtually. Right, so thank you very much. For the final group, we won't have a class tomorrow. There's no class tomorrow because I'll be in a conference, virtual conference, whole day. So tak ada class. So I'll see group number 8 presentation this Wednesday. Okay. So we'll finish off the presentation this Wednesday. And then on Thursday, I'm going to start talking about MOSFET for perhaps 2 sessions, Thursday and Monday next week. And then hopefully you'll finish by Monday, and then no class for Tuesday. You're gonna have a class. You're gonna have a test on Wednesday, right? 30th kan? 30th is Wednesday, isn't it? So yeah, 30th Wednesday. So I'll try to finish by Monday on MOSFET. So and I'll give you free time on Tuesday, and then you're gonna have your test to open book on Wednesday, right? So no class for tomorrow. I'll see you Wednesday this week for the final group presentation. Bye-bye. Take care. Assalamualaikum. Azwani, nanti please email to me your slide, yeah? PDF.
Thank you, Doctor.
All right. Thank you.